So let's talk about Archimedes' principle for a minute. Archimedes' principle says that the buoyant force equals the weight of the displaced water, and I'll just show you that in a second. Archimedes was given the job by his king, Hieros maybe, to determine whether the king's crown was made of gold, as it was supposed to be. Archimedes was supposed to find if it was truly made of gold. And what Archimedes realized was when you submerge something, the buoyant force on it equals the weight of the water displaced. And he used that to take an equivalent weight of gold to the crown. So he weighed the crown, he found an equivalent amount of gold, and since the crowns were those leafy, viney looking crowns, he couldn't exactly determine the volume. And so he put it on a balance underwater with an equal weight of gold. And since they would displace the same amount of water, they should balance underwater. But if it was made of something other than gold, it would displace a different amount of water than the gold would and wouldn't balance. And so it's just a simple seesaw type balance with an equal amount of gold that he used, put them underwater, and showed that the crown didn't balance, and so it wasn't made of gold. So here's the idea. The buoyant force equals the weight of displaced water. We all know that when we submerge something underwater, it weighs a little less. And so I'm just taking an imaginary cylinder here that's in water. It can be a real cylinder, but we can just take an imaginary section of water here shaped like a cylinder. There's the surface of the water. And so the top of the cylinder is a distance h1 below the surface. And the bottom of the cylinder is a distance h2 below the surface. And so there's a pressure on the top part of the cylinder that's due to being h1 below the surface. And so there's a force on the top part of the cylinder. And the force we call F1 is just the pressure times the area. And the pressure at this depth is just rho g h1. We already learned that. And so the downward force on the top is rho g h1 times the area. That's what's pushing down on it. And you can just think of this as an oil drum or something like that. But you can also just think of it as an imaginary section of water. Right? There's a section of water, just a cylinder of water that's stationary in the pool, and we're just looking at it. And so the bottom of the cylinder has an upward force. We learned from Pascal's principle these forces act in all directions from the pressure. And so the force on the bottom is the pressure at the bottom times the area of the bottom, which is the same as the area of the top. So I don't need an A2 and an A1. It's just got a regular shape. And so that's the pressure at the bottom, which is rho g h2 times the area. And so the force on the bottom pushes up, the force on the top pushes down. The net force is the buoyant force. It's F2 minus F1. And so we calculate that that's rho g h2 times the area minus rho g h1 times the area. That's what we got for those two forces. Right? And if I do a little math on that, I get rho g times h2 minus h1 times the area. Well, h2 minus h1, right, is just the height of the cylinder. h2 minus h1. Didn't write that very well, but you get the idea. Try one more time. h2 minus h1. Right, and that's the height of my cylinder. And so the height of the cylinder times the area is just the volume. And so the buoyant force is the density of the water. Again, the density in these things is the density of the fluid, whatever it's in, times g, times the volume of the cylinder. And so that's just the mass of the water that's been displaced. The density of water times the volume of the cylinder is the mass of the water that's been pushed out of the way. When I multiply that by g, I get the weight of the displaced water. And so the buoyant force equals the weight of the displaced water. So we can use Archimedes' principle to look at the fraction submerged for objects that float. If I have some object that's floating on the surface, other than bobbing, if the water's still, it'll just be stationary on the surface, and there's two forces acting on it. It's got the buoyant force pushing it up, and it's got gravity pulling it down. And so if I just use Newton's second law and say the sum of the forces in the y direction, right, if this is my y direction, is equal to mass times the acceleration in the y direction. If it's at rest, that's 0. then the two forces, the buoyant force minus the weight, is 0, or the buoyant force is equal to the weight. So now I can break these down. I can say, well, look, the buoyant force is the density of the fluid, probably water in this case, but it could be anything, times the volume submerged. Remember, it's the weight of the displaced water, and so it's just the stuff that's underwater is the volume submerged. It's not the whole volume of the object, right? Times g, that's the weight of the displaced water, right? Equals the weight of the object. Well, that's the density of the object times the volume of the object times gravity, right? And you can see that gravity cancels on both sides, and I get these two things are equal. And so if I divide by the volume of the object on both sides and I divide by the density of the fluid on both sides, I should call this fluid because it doesn't have to be water. Most of the time I'm assuming it's water. Then this is the fraction submerged, right? The fraction submerged is the volume submerged divided by the volume of the object. That's just what the fraction submerged is. Well, that's just equal to the density of the object divided by the density of the fluid. And so if you know the two densities, then you know what the fraction submerged is going to be. So for example, the density of ice over the density of water is 920 kilograms per cubic meter over 1,000 kilograms per cubic meter. And so that's 0.92. And so that's the fraction submerged for ice. When you put ice in water, 92% of it is underwater. Somebody should have tipped off the captain of the Titanic. I'm just kidding. They do that. All right. So this is determining the density of objects that sink. We just did an example on determining the density of objects that float. And so what you do is you take a spring scale, that's what these are supposed to be, and then you can weigh something with a spring scale. This is a cup I've drawn. It's because it's what I used in the example. And so I can weigh use the spring scale to weigh the cup out of water, and so I call the upward force from the spring scale, which is what the scale reads, is T out. It's the tension out of water. And I think in the example we did, it was 2.8 newtons, but it doesn't matter. We can just pick a number for that. Well, we would read it if we were doing an experiment, right? And then that's balanced by a downward force, which is the weight of the object. If I do the sum of the forces in the y direction, I get T out minus the weight is equal to 0, or the tension, the thing that the scale reads, this little red line, is equal to the weight of the object. Well, that's what we expect. That's how we weigh objects, right? I can do the same thing in water. I can say, if I weigh the object in water, if I just take this thing and lower it so that the cup is underwater like I did in the video, you'll notice that the weight reads less. And that's because you're not really weighing it anymore. You're reading the tension when it's submerged, and the tension in the spring is being helped by the buoyant force. And so if I do some of the forces again here, now I get the tension in water, which is the upward force from the scale, plus the buoyant force, which is helping it, minus the weight, equals 0. And so here, the tension in water is the weight minus the buoyant force. The tension out of water is just the weight. And now I can just do a simple calculation. I can say I'm going to evaluate T out over T out minus Tn, and it's easy because it's just this divided by the difference between these two. So I can evaluate that really easy by weighing something in and out of water, or in and out of any fluid. If I just plug in the values I got here, the equations I got here, it becomes mg over mg minus fb, or just mg over fb, right? And what's interesting about that is the top line is just the density of the object times the volume of the object times gravity, because that's the mass and that's gravity. And the bottom line is the weight of the displaced fluid, which is the density of the fluid times the volume of the object times gravity. Well, the volume of the object times gravity cancels, and this quantity becomes just the ratio of the density of the object to the density of the fluid. And so I can evaluate that. For our case, I take 2.8 newtons over 2.8 newtons minus 1.2 newtons, which is 2.8 over 1.6. The units cancel, is 1.75, is equal to the ratio of the density of the object to the density of the fluid, or the density of the object is 1.75 times the density of the fluid. If it's water, then the density of the object is 1,750 kilograms per cubic meter. And what's neat about that is that I've taken an oddly shaped object whose density I would have a very difficult time calculating the traditional way where you do density as mass over volume. I would have to figure out some way to evaluate the volume of this. But I can just do this simple measurement and determine density. And so it's pretty useful.